Welcome my dear friends, a very good morning, good afternoon, good evening to all of you. Welcome to this NPTEL MOOC course titled Data Analysis and Decision Making. And as you know, this is a course for 12 weeks and this total number of hours is 30 hours, total number of lectures is 60. And each week we have 5 lectures, each being of half an hour. And if you remember, we have just finished 30 lectures, that means we have just completed half of the whole course, and that means half of the whole course took about the whole portion of very keeping it to very brief, the whole portion of univariate statistical methods in a very simple way. And if you remember that in the 30th lecture, the beginning, for about 15 minutes I gave a wrap up of what we have discussed and how we have proceeded. So, if you have understood all the concepts in the 30 lectures related to univariate statistics, I do understand many of the things were done in a manner so as to give a brief outline. But based on the fact that you have inculcated in within yourself an interest for these topics, please read the book, please read any good textbook, especially for the colleges, for engineering colleges, for statistics, which are more applied in nature, because this I do remember mentioning it time and again. This is not a theoretical DADM1 or a statistics course. It is more to do with application and how the concepts are utilized. And then also I urged in the 29th lecture, in the 30th lecture also, please give us feedback to us about how the course is going on, how you are feeling comfortable with the level of coverage, whether they are becoming interesting, the coverages are fine, whether the examples are fine, such that and whether how the assignments are, such that we can also learn and make this course in a much better fashion for all of you who really want to learn. Now, if you remember that in the 30th lecture I was basically discussing the different type of metric or different type of characteristics for the multivariate statistical distribution. We discussed the mean, we discussed the standard deviation, we discussed the sample mean, we discussed the sample standard deviation, which was the error, and what were the symbols like mu, the variance covariance matrix, then x bar being for the sample counterpart, s being the counterpart in the sample for the variances. They would be counterpart for the skewness curtices also. So, now if you remember, I did discuss about the correlation matrix being the relationship between the random variables, and correlation matrix would be in the range of -1 to +1, 0 being the case when they are not correlated, greater than 0 and till +1 would be the case when they are positively correlated, and less than 0 and greater than -1 would be the case when they are negatively correlated. So, the correlation matrix again would be of size p cross p, where the principal diagonal would obviously would be the correlation, first element would be the correlation of the first with itself, second element would be the correlation of second with itself, so on and so forth. So, the principal diagonal would all be 1 and the off the diagonal element would be the correlation coefficient existing between the ith and the jth. The upper half and the lower half would be the correlation of the jth to the ith, so they would be symmetric to each other. So, while the sample counterpart would be given by capital R, which is again size p cross p, and again the sample counterpart, the correlation for the sample, the principal diagonal again would be 1, and the off the diagonal element would be the correlation coefficient from the sample perspective for the ith to the jth in the upper half, and the lower half across the principal diagonal would be the correlation coefficient of the jth to the ith, and they are symmetric if you remember. Now, if you want to find out the mean of the jth random variable, and if it is a discrete case, you will basically multiply the corresponding realized value x j. So, here it is. So, you will basically sum them, and what you will sum is basically this: the realized value, which is xj, for all j's. So, obviously it will be x j1, j2, j3, j4, so on and so forth. j1 with the first reading, j2 to be the second reading, j3 be the third reading, with j denotes the random variable number, and 1, 2, 3, 4 basically denotes the realized value. Multiply by its corresponding probability. So, this is what it is: P probability of xj is equal to small xj, which is basically probability of capital Xj is equal to small xj1 or small xj2 depending on the case, and you will basically multiply that corresponding value probability with the realized value. So, if I write down the formula, so it will be xj, say for example, let me use the index of L, probability xj is equal to xj L. So, for all, so it would be xj1 probability xj is equal to xj1 plus, I am basically writing here below, the second part would be xj2 probability xj is equal to xj2, and will go on till that number of terms, and you add them up, that becomes the expected value. While if it is a continuous case, you have to basically integrate it. So, the integration would be, in the case, let me erase it. For the case when it is a continuous distribution, integrate it for all xj, and it will be xj f of xj dxj. So, basically you find out the probabilities for all and find out the sum, which is integration exactly like this, and you will find out the expected value, while the sample counterpart, as I have already told, that will be the sample average. So, multiply the corresponding values for the xij's. So, I being from 1 to n number of observations, add them up, divide by 1 by n. Here 1 by n basically means the corresponding relative frequency or the probability for the xijth element. So, if all of them are of equal proportions, the probability would be 1 by n. Add them up, divide by n, and get x bar j. Now, if I consider the covariances, so covariance existing between jth 1 and jth 2, j suffix 1 and j suffix 2 basically denotes the random variable given by the notation of j1 and j2. That if obviously we know that the covariance concept gives us the formula that it is equal to the expected value of the multiplication of the differences. So, what are these differences? In case the differences are, so if there are two random variables, in the first case the differences are with the random variable xj1 with respect to its mean value. So, all the realized value as they are changing, I take the mean the differences, and in the second case it is basically again the differences of all the random variables of j2 with respect to its own mean value, which is x mu j2 or x bar j2, whatever the case is. So, that is given by the covariances, and the corresponding variances are when both xj1 and xj2 are same. So, they would basically be the principal diagonal, and we can find them out. And in the case when you have the continuous for the continuous case you will basically double integrate, there will be double integration. Only remember one important thing, the integration would be for the case when you want to find out xj1 minus its expected value multiplied by xj2 minus its expected value, but the f of x would now be replaced by f of x j1 and j2, because that is the binomial distribution based on the fact that x1 and x2 are random variable. So, based on that you find out the covariances for the continuous case, and similarly the counterpart of the covariances for the sample would be again given by 1 by n minus 1, provided you lose 1 degree of freedom, and the multiplicative term are xj1 minus its sample mean multiplied by xj2 minus its corresponding sample mean. Similarly, covariances can be found out by the ratios of the covariance of xj1 j1 and j2 divided by the square root. In one case there would be two square roots. So, the square root would be the variance of of j1, and second one would be the variance of j2, which is the other one. So, while the sample counterpart, which will be denoted by small r. So, if you remember the capital R, that was basically the matrix corresponding to the correlation coefficient for all the p number of variables. So, this sample counterpart rj1 and rj2 would be equal to the covariance of the samples, which is in the numerator. So, this would be mimicking this. This one would be mimicking this one, and this one would be mimicking this one. So, once you have this ratio, you can find out the correlation coefficient existing between two random variables. So, now we see the co-skewness. Obviously, we did not go into details, but I am just giving this definitions just for your own interest. So, the co-skewness basically consists of the case where you find out the third moment help based on the fact that I want to find out the co-skewness between J1 and J2 and J3. And in the case when if it is a discrete case, you will basically find out the differences between the J1 in its mean value, J2 in its mean value, J3 in its mean value, multiply them, and then multiply by the corresponding multivariate values when xj1 is equal to x1 xj1 small xj1, capital Xj2 is equal to small xj2, and capital Xj3 is equal to small xj3. Based on that fact, how the probability changes, we multiply the probability to find out the co-skewness. In the case if it is a continuous distribution, rather than finding out the sum, we replace it with the corresponding integration. So, the integration is given. I am just highlighting the relevant part. So, this is for the second one. If you see the coloring scheme, you will understand which variable and what are the counter points or the formulas based on which you are doing the calculation. And obviously, this is the joint distribution of x1, x2, x3, and remember, co-skewness is related to skewness in the same way as covariance is related to the variance. When we found out the skew relationship, the correlation coefficient. Now, the skew relationship again is basically the co-skewness divided by the square root 3 terms. So, the first square root is basically the standard deviation of the J1, then the second element is basically the standard deviation of J2, and third element is basically the standard deviation of J3. Based on that, we divide the skewness by these values, which are technically the standard deviation of 1, 2, 3 multiplied, you divide and you get the skew relationship. Now, co-kurtosis basically is again the same thing, but you only increase the number of random variables. So, in skewness you had 3, now you have 4, x1, x2, x3, x4. So, in the case if it is discrete, again you follow the same rule, find out the difference between the random variables, the realized value and his expected value. So, this would be true for the first random variable, second random variable, third random variable, fourth random variable. In the case if it is discrete, you multiply them by the corresponding probability, add them up. In the continuous case, you integrate it, but the joint distribution of all the 4 random variables should be considered, so that we get the value of the co-kurtosis. So, similarly, co-kurtosis is related to kurtosis as covariance is related to variance. I did mention that, so in order to basically bring a simile or the understanding how things are done. And then again you have the quartic relationship. Quartic relationship would basically be the same concept. The co-kurtosis would basically be on the numerator, and in the denominator obviously you will have the standard deviation of the first, standard deviation of the second, standard deviation of the third, standard deviation of the fourth, and based on that you will basically do your problem. So, now we will consider the data set related to cigarette smoking, which is given in Statistics for Engineers and Sciences by William Mendel Hall and Terry Sinchis. So, this is a Pearson publication 2006. The data set contains measurement related to brand, tar content, nicotine content, then the weight and carbon monoxide content for 25 brands of cigarette. So, the data set can basically be accessed in the American Statistical website, which is amstat.org, and you have the publication. Based on that you can find out the data. So, consider there are basically 4 variables P1, 2, 3, 4, which are x1, x2, x3 and x4, which are basically the tar content, the nicotine content, the weight and carbon monoxide content. So, based on that, if we have for the 252 data sets, put them, find out the correlation coefficients and the values as rightly shown in this diagram. The principal diagonal is all 1, because they are the correlation of the first to first, second to second, third to third, fourth to fourth, and the off the diagonal element are the correlation existing between the first to second, first to third, first to fourth. Similarly, for second to first would be the counterpart on the mirror image, then it would be second to third and second to fourth. Similarly, you can find out all the correlations, they would be mirror image. So, as pointed out, so let me show this one are same, this one till 8, this one, this one, this one. I am just showing you the mirror image concepts. Oh, sorry, this would be the case. My apologies. So, they are the mirror image and you have found out. So, they can basically give you the relationship correlation coefficient existing between the terms. Furthermore, utilizing R, we get the multiple correlation coefficient factors. So, which are given as 0.9867 till the first one till 0.9584, while the corresponding R square values, what are these, I am going to come back to that later on. And the corresponding R square values are 0, I will only read the first two decimals, which is 0.97, 0.95, 0.53, 0.91, and based on that you can do the calculations accordingly. Simple calculation will also yield the partial correlation. Now, remember the important fact, the partial correlation coefficient and the full correlation coefficients are different. So, partial correlation is exactly something to do with the fact that I am keeping all the other variables fixed and basically trying to change the one of the variables, and based on that I am trying to find out the partial correlation coefficient. So, partial correlations would be basically the relationship between two random variables provided others are kept fixed. So, the partial correlation coefficient matrix is given, again it is a mirror image. So, the first one, second one, I am just highlighting it, third one. So, these are the elements in the partial correlation coefficient matrix. To double verify the calculations, we may also calculate the partial regression coefficients and solve our problem, but I am not going to come into these details as of now. So, we will consider the multinomial distribution for the multivariate case. So, suppose x1 to xp be p jointly distributed random variables, each of which is discrete, non-negative and integer valued. Then the joint probability mass function. So, now what you have, if you remember the binomial case, there were two random variables. Now, in the multinomial case, you will basically, in a trinomial you will have three random variables, and the Bernoulli trials and all these things would hold true. That means, the values of the random variables x1, x2, x3 would be coming out, the corresponding probabilities would be independent from throw to throw or roll to roll or the outcomes, and the corresponding sum would also be 1. That means, if the probability is p1, p2, p3, sum of that p1, p2, p3 would be 1, because there has to be any one outcome out of the 3 considering the trinomial distribution, and we will find out the corresponding distribution for the case for the multinomial case. So, as I was saying, suppose x1 to xp are p jointly distributed random variables, each of which is discrete, non-negative and integer valued. Then the joint probability mass function of x1 to xp is called the multinomial distribution of the form. So, here the form is, so it is, what have I written, I am just trying to highlight, this is NC x1 xp, and the probability case is p1 to the power x1 multiplied p2 to the power x2, it is pp to the power xp, and the sum of p1 plus p2 plus is equal to 1, that is true. And this formula which I have written is for the case of this distribution. So, this is the multinomial case. So, probabilities are given by p1, p2, p3 till pp or pk, whatever it is, and the corresponding numbers are basically given as x1 and x2, x3, x4 till xn. So, for a better appreciation of the multinomial distribution, consider the polynomial coefficient or expansion of the multinomial case. So, the polynomial expansion would be for p1, oh, sorry, I am using the highlighter, my mistake. So, it will be p1 x1 plus p 2 x2 plus pp xp expanded in the multinomial case, and you will get the multivariate distribution. Now, a closer look at the expansion will make it immediately evident how the polynomial coefficient of multinomial expansion corresponds to the multinomial distribution as case. And another interesting fact is basically its analogy with the multinomial distribution has with the Pascal pyramid. So, Pascal pyramid is a pyramid and with 3 sides, it looks like this. So, the slices which are there in red color, green color, light blue, violet, yellow, dark blue are as you expand the numbers higher on. So, as you go for the higher numbers of the Pascal values, as you go down technically, they would basically correspond to the fact that you have higher values of n. And if you basically take the slices as I mentioned as represented by A, B, C, D, E, F of the Pascal pyramid as a flat triangular plates. So, they are basically a pyramid of 3 sides, the base is also a triangle, not the square one. Then the numbers depicted on them would be as follows. So, they would basically give you the numbers for the polynomial expansion. The first one would be corners would be 1 1 1, second corners which is the green slice which you have taken would be corners would be 1 1 1 and the midpoints would be 2 2 2. So, they are corresponding to the coefficients. In the third case blue one, you will have corners again 1 1 1 and the midpoints would be again between the sides of the triangle 3 3 3 and the middle point where the intersections happens for the 3 is 6. So, they are basically corresponding to the coefficients of the multinomial polynomial expansion. Similarly, for the other case triangles for the fourth level A, B, C, D. So, you will basically again the corner points as 1 and the in between points of 4, 6 and 12 would basically corresponding to the values of the polynomial coefficients. So, with this I will close the 30th lecture and continue the discussions of the multivariate distribution in the corresponding one, and go a little bit slow because there are a lot of concepts to be covered, and we will try to basically make it more hands on depending on definitely the feedback which you give, and I am sure it will be helpful for all of us to make it in the right fashion. Thank you very much with this your attention and have a nice day. Thank you.